Today's lesson on thermochemical equations allows us to integrate a little bit of balanced equation writing in terms of endo and exothermic reactions just by adding a little piece of information called the delta H, the enthalpy. Think of that delta H as the change in heat content as reactants turn to products. Tools that I'm going to ask that you have out as you listen and fill in your notepad with me. Notepacks are open to page 5, about halfway down where we left off. We'll see a title called Thermochemical Equations. Pause the video and open your notepad to page 5. Another tool you will need out, you'll need a calculator. We'll be hitting a little bit of some stoichiometry, looking at want over given, inviting in kilojoules into the heart of our stoichiometry roadmap. Perhaps you also like out your stoichiometry map to help guide your pathway in problem solving. Other tools, of course, would need your periodic table polyatomic ion chart because we will be writing formulas to write balanced equations. So the normal tool pages, and I'll just ask that you pause this video until you're ready with the tools that you need for success. As we begin thermochemical equations, we wanted to define the term for us, and it's written for us right in our notepad. It shows the thermochemical equation simply by adding on the heat content. So just reading for you right in that bullet, it was on the first slide, shows the thermochemical equation including heat content, the delta H, the enthalpy of our reaction. And we'll dive right in to illustrate. We want to show a thermochemical equation for calcium oxide reacting with water, and here's an important word, releasing 65.2 kilojoules of heat energy. I've made releasing capital. I remember exothermic heat releasing, delta H will be negative. The system loses heat to the surroundings. We'll show that with a negative sign. Of course, step 1, we have to always stay solid in our equation writing. We have to turn calcium oxide reacting with water into a balanced equation. Find your helpful hint combination pattern page. Review that to try to commit to memory. I'm not asking you to memorize them, but boy, the more you become familiar, the faster you become in equation writing. Sometimes speed on a test is our worst enemy, and speed and proficiency go hand in hand. So commit to memory best you can the helpful hints. At least acknowledge having them close by. Helpful hint number 4 on the combination. It's going to tell us about a metal oxide combining with water, forming a base. Read it again, but instead of putting the word metal oxide, put in the word calcium to help you see the skeleton of our equation. When calcium oxide reacts with water, it forms a base called calcium hydroxide. Those are the words for the skeleton we have to place in our notepad. Calcium oxide, Ca is a +2, oxide with a -2, we can see CaO becoming the formula for calcium oxide. Its adjective is a solid. When placed into water, forms a base. CaOH taken twice is the formula for calcium hydroxide. Ca is a +2, the polyatomic ion hydroxide a -1, so I've just crisscrossed, and this equation comes out balanced. So we have a balanced equation with 1:1:1 stoichiometric ratio. The next step of our lesson is to turn this balanced equation into a thermochemical equation, and that's simply done by adding the delta H information at the end of our sentence. Recall the word clue, releasing. It clearly said releasing 65.2 kilojoules of heat, and I'll often say just kJs, kilojoules, abbreviated. At the end of our chemical sentence, we say the change in enthalpy is negative 65.2 kJs. At the bottom of our slide is our completed, corrected answer. In a combination pattern, exothermic heat releasing, we would interpret this equation by reading 1 mole of CaO combines with 1 mole of water to form 1 mole of CaOH taken twice, calcium hydroxide. And that process absorbed 65.2 kilojoules of heat. Delta H, fancy vocab, enthalpy, E-N-T-H-A-L-P-Y, enthalpy. Think of it nothing more as the heat exchange from the system to the surroundings. We can diagram this in what's called an enthalpy diagram. Now, an enthalpy diagram on our knowledge wall posters above the board in our classroom, it's simply an XY coordinate, an XY axis that shows heat content labeled on our Y axis, and heat is always measured in kilojoules, and time will be placed on the X axis. Simply placed, it says as time goes by, reactants form products, and we keep track on this coordinate the exchange of heat from the system to the surroundings. So the reactants and products are simply separated by their energy content on an XY grid. Let's model an XY axis called an enthalpy diagram for the reaction we just wrote down, the formation of the base calcium hydroxide in our combination pattern. Clearly it showed it was an exothermic diagram. So I'm showing the reactants losing heat energy as they form the products. Simply draw an XY coordinate as shown on this diagram. I placed the words heat content, the unit would be a kilojoule, on the Y axis. Notice the direction of our reaction stays the same. The reactants will always point at the products, just as we has written a moment ago. But I'm simply separating the reactants and products by the heat content. The reactants have higher heat content because they are losing it as they form product. So simply placed, up high, draw a line and place your reactants, CaO plus H2O. Draw an arrow down at your product, Ca parenthesis OH taken twice. As the reactant turns to product, we see a heat loss of 65.2 kilojoules. Place the delta H next to your arrow as I have done on the slide. The heat that separates the contents of CaO and water is negative 65.2 kilojoules. When you have that, we'll try another. Pause the video if needed to catch up. When we look at our next example, it reads, the thermochemical equation for sodium hydrogen carbonate is decomposing. Now that's a clue that decomposition helpful hint page might be there. So you have it out a moment ago for your combo. Make sure it stays handy as we're writing all kinds of equations today. We're going to decompose sodium hydrogen carbonate, and it tells us the product sodium carbonate, water, and carbon dioxide. A clue here is that it's absorbing 129 kJs of heat energy, kilojoules, I'll abbreviate as kJ. Absorbing tells us that we have an endothermic process. I need us to be comfortable in grabbing our periodic tables, the polyatomics, and I've got to have you ready to write a balanced chemical equation. That's a solid foundation carried forward in every new unit coming up our way. That just never goes away. Grab your polyatomic, pause this video, and get your skeleton placed and work to balance it. That first reactant, sodium hydrogen carbonate, you found sodium as Na and it carried a +1. On your polyatomic chart, you found hydrogen carbonate, and we handwrote that we also sometimes call that bicarbonate. That's probably handwritten on your chart. You found it to be HCO3 carrying a -1. Put it together and you formed your formula for our reactant, sodium hydrogen carbonate, or it could be called sodium bicarbonate as NaHCO3. You place that as a reactant. Decomposition means a single reactant breaking down. So now you're making your first product, the sodium carbonate. Sodium we know is +1. Polyatomic carbonate, that's the middle column of your chart. Find that, you'll see that it carries a -2. And when you crisscross, the first product you formed was Na2CO3, sodium carbonate. The other products are familiar to us: carbon dioxide, CO2, and water, H2O. How's your skeleton looking so far? When you balanced, you needed to double the reactant, and we came out with a 2:1 to 1:1 stoichiometric ratio. Our balanced equation needs to turn into a thermochemical equation, and that simply means add on the delta H information, the heat of reaction, to the end of our chemical sentence. Notice that the problem said it absorbed 129 kilojoules of energy. Absorbing represents an endothermic process. Endos have a positive delta H symbol. We're absorbing heat into the system. To turn our balanced chemical equation into a balanced thermochemical equation, we simply tack on the delta H information to the end of our chemical sentence. Our complete correct answer for our thermochemical equation for the decomposition of sodium bicarbonate is shown in the last sentence of our slide. 2 moles of sodium bicarbonate decompose to form 1 mole of sodium carbonate, 1 mole of carbon dioxide, and 1 mole of water. This process absorbed 129 kilojoules of heat. We're being asked to show this process on an enthalpy diagram. The enthalpy diagram simply shows an XY coordinate that separates the reactants and products based on the heat loss or gained of a system. When the heat is lost, exothermic, and in our last example, we showed the arrow pointing down with a loss of delta H. In this example, since it's endothermic, we're gaining heat into the system. Therefore, you see the delta H pointing up. As the reactant down low forms the products up high, the system gained heat. We are separating the reactant from products by 129 kilojoules of heat. Now friends, it doesn't matter to me how you arrange them. We just have to be sure down low on the X coordinate is the reactant. Draw a line up higher to form the product, and just label that distance between them as 129 kilojoules of heat. Very important to notice on the 2 diagrams. Pause a minute and carefully examine. The first diagram we drew was exothermic. Reactants point down to products. It's a heat loss. The second, the one we're looking at right now, is a gain of energy by the system. Endothermic points up as the system gains energy to form the products. Exo loses point down. Endo gains point up. The enthalpy diagrams will be an entire objective on our next test, Objective 2. Just simply writing balanced thermochemical equations and drawing their enthalpy diagrams. A new skill is to incorporate the kilojoules from our balanced thermochemical equations into some stoichiometric values. And this is the 3rd testable objective on our test, doing a little stoichiometry with kilojoules. It's not any harder than a want over given mole ratio. So to solve our problems involving thermochemical equations, we treat the enthalpy value, that's kilojoules, as any other stoichiometric value. On our stoichiometry roadmap, in the heart of our problem, when we say want over given, we've always said that those want over givens are the coefficients from the balanced recipe. Well, now we're saying not only can they be coefficients, they can also be the kj's from the balanced equation. So you may choose to actually write that directly on your stoichiometry roadmap. In the heart of the problem, want over given may stand for a coefficient, or it may stand for the kilojoules from the balanced equation. Same problem, thinking want over given, where the want can stand for the coefficient or for the kilojoules. The same is true for given. So when we write want over given, we might take a coefficient or we might place in the word kj. Let's model some of these to show you how much you already know going in. We've turned our paper to page 6 in the notepack, and we see a series of examples we're going to work through together. Let me read for us number 1. Please follow along. Using the equation from above, calculate the kilojoules of heat required to decompose 2.24 moles of sodium hydrogen carbonate. The equation from above is the equation we just finished drawing the enthalpy diagram for, the decomposition of sodium hydrogen carbonate. So on your paper, leave yourself room to work as well, just rewrite the balanced equation just as we had completed it a moment ago. Recall that it was endothermic, so our chemical sentence, the recipe for the stoichiometry problem, 2 NaHCO3s form Na2CO3 plus CO2 plus water, and the delta H is 129. Honey, that gets picked up. Interpreting that equation, it says when 2 moles, see that coefficient, 2 moles of sodium bicarbonate decomposes, 129 kilojoules of heat is absorbed. Here's the stoichiometric ratio. 2 moles of sodium bicarbonate absorb 129 kJs. Notice the 2 is the given, the 129 there is our want. 129 kilojoules of heat is absorbed when 2 moles breaks down. So how many would be absorbed if 2.24 moles of the reactant decomposed? You can see it's just a simple want over given ratio. Write down, as we always do underneath that recipe, the unit given, 2.24 moles of NaHCO3. We're right directly in the heart of our problem, the want over given, where I simply want kJs given a mole unit. The want over given ratio needs to cancel mole and bring us to kJs. Remember the want, go up to the balanced equation. The want is kJ. From the recipe, it's 129. Positive to remind us it's endo. Given is the number in front of our reactant, the 2 moles of baking soda, NaHCO3. The want over given ratio comes from the balanced equation, as it always has. 129 kJs of heat per 2 mole of baking soda, NaHCO3. Let's put it together in a familiar format of problem solving. We wrote down 2.24 mole of baking soda, NaHCO3. That was the given quantity. We set up a want over given ratio. That's coming from the heart of the stoichiometry roadmap. From the balanced equation, we want heat. Its value is positive 129 kJs of heat. Given the quantity of baking soda, its coefficient is a 2. The heart of our problem, the want over given, is positive 127 over 2 with the correct labels. kJs of heat per mole of baking soda. Hit that on your calculator to confirm the answer. Don't wait for test day to make the calculator your friend. Hit it now to confirm you can get the same thing I did. Example 2. When carbon disulfide is formed from its elements, 89.3 kJs of heat is absorbed. Calculate the amount of heat in a kJ absorbed when 5.66 grams of carbon disulfide is formed. Through the first read-through, I just need to pull out the recipe. I don't care about the numbers until I can get a balanced chemical equation. Pause the video and work to write a balanced equation. Listen to the prefixes. Carbon disulfide is formed from its elements. Turn that into a balanced equation, then tack on the delta H to get a balanced thermochemical equation. Pause and work to write that equation. When ready, start up. How'd you do? Carbon disulfide is formed, so it's a product. Notice we had to point at it. CS2 is the product. The elements it's made from, carbon, its symbol C, sulfur, symbol S. Neither belong to the lucky 7, I need a diatomic molecule. And heat is being absorbed, so we clearly see delta H as a positive value. My balanced thermochemical equation, carbon plus 2 moles of sulfur form 1 mole of carbon disulfide. The heat of reaction is a positive 89.3 kJ. The change in enthalpy, I'll say heat of reaction interchangeably. Delta H is called enthalpy, the heat of reaction. This reaction absorbed heat. Now that we have that recipe placed, we can go back and figure out what it is we're being asked. Knowing the recipe tells us for every 1 mole of carbon reacting with 2 moles of sulfur, we form 1 mole of carbon disulfide. Coefficients stand for moles. But now also we have kJs introduced. That process absorbs 89.2 kJs of heat. So, what if we started with 5.66 grams of the product? We know 1 mole of product relates to 89.3. How many kJs of heat? We're given a mass, want to calculate the heat. Given a mass, calculate the heat. On our stoichiometry roadmap, it would be a step 1, step 2, then stop. Step 1, grams into moles. Step 2 is our ratio. Step 1, step 2 will bring us from mass to kJs on our stoichiometry roadmap. Start by writing the given. 5.66 grams of carbon disulfide, the given quantity. Our first conversion is nothing more than an old mole map conversion. We'll use the molar mass of our product carbon disulfide. Add a carbon. Its molar mass is 12. I'm going to check mine. Carbon is 12. Plus sulfur is 32, but there's 2 of them. And I do indeed get the 76. So there's the molar mass, 76 grams. Step 1 on the roadmap. Step 2, a want over given ratio. Always pulled from the balanced equation. That's no different than in the last chapter. However, this time we want kilojoules of heat. Its value from the recipe, 89.3 kJs of heat. I place the positive to remind us it's absorbing. It's endothermic. The coefficient in front of the product is a 1, so 1 mole of CS2. A want over given ratio. Step 1 cancels grams. Step 2 cancels mole. Hit it out on your calculator. 5.66 divide by 76 times 89.3, and we find 6.6505 kilojoules. Positive because it's endothermic. Step 1, step 2 on the stoichiometry roadmap. We have a third example. I'll read through. The production of iron and carbon dioxide from iron 3 oxide and carbon monoxide is an exothermic reaction, releasing 26.3 kilojoules of heat. How many kJs of heat are produced when 100 grams of iron 3 oxide reacts with excess carbon monoxide? First step when I read a problem like this is to get out the balanced equation. Don't worry about the numbers. Think about the balanced equation. It says production of iron and carbon dioxide. That means their products. Point at them. Make iron and carbon dioxide. Make it from, so here's the reactants. The iron 3, iron's a +3, oxide a -2, and carbon monoxide. 2 reactants forming 2 different products. Pause the video, work on your skeleton, get it to balance, and then place the delta H information. When ready, start up again. How'd you do? The balanced thermochemical equation. It says iron, symbol Fe, and carbon dioxide, symbol CO2, are being produced. Are they on the right side of your equation? The iron 3 oxide formula, Fe2O3, and carbon monoxide formula, CO. Did you place them on the left side of your arrow? The delta H information says releasing. Did you make the delta H negative for exothermic? When you balanced, it involves some 3's. Take a look and see how well you did. 1 mole of Fe2O3 reacts with 3 moles of carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. A 1-3-2-3 balances that equation. And the delta H exothermic, it released 26.3 kJs of heat. The kilojoules of heat is exothermic. If we know 1 mole of iron oxide releases 23.6 kJs, we're being asked to calculate how many kJs of heat are released if we started with 100 grams of the iron 3 oxide. Given a mass, calculate the heat. Very similar to our last problem, a step 1, step 2. Step 1, divide by the molar mass to bring it into the mole. Step 2, bring it want over given ratio. Given 100 grams of the iron 3 oxide, how many kilojoules of heat are released? Always start with the given quantity, write on your paper 100 grams Fe2O3. In the first conversion factor, it's step 1 on our stoichiometry roadmap. We need to go from the gram into the mole, so we use the formula weight. We call that the molar mass of our reactant, iron 3 oxide. Iron at 55.8 doubled plus 16 times 3. That does indeed add to 159.6 as the formula weight of rust, iron 3 oxide. Step 1 cancels the grams. Step 2, the heart of our problem, the want over given ratio. We want kJs. From the balanced equation, the end of your sentence, it says negative 26.3 kJs of heat. The coefficient for the reactant, iron 3 oxide, is a 1. The want over given ratio, I want kJs, negative 26.3. Given iron oxide, its coefficient of a 1. Hit that. 100 divide by 159.6 multiply by negative 26.3 equal. See if your answer matches mine. Be sure to record the negative for the exothermic quantity. The last example for our stoichiometry, we'll read for example 4. combusting 1 mole of methane. Methane is natural gas, CH4, the simplest organic hydrocarbon. Releases negative exothermic, 890 kJs of heat. Plenty of sentence right there to go to work to write a balanced equation, dusting off your combustion patterns. We have to be able to turn that that sentence into a balanced equation and then tack on the delta H information. Combust methane. That means add oxygen, out comes carbon dioxide, water. Balance it and tack on the delta H. We'll be calculating for grams of methane needed to release 1250 kJs of heat energy. Pause the video and balance your thermochemical equation. How'd you do? CH4 combusts with oxygen to form carbon dioxide and water. The delta H, negative 890 kJs. A 1 to 2 to 1 to 2 stoichiometric value. We know that 1 mole of methane releases 890 kJs. How many grams of methane would be needed to release 1250 kJs? This is the opposite direction of the previous two examples. Given the kJ, we're actually in the heart of our problem. This particular stoichiometry journey, if you'd like to see on your roadmap, involves a step 2, step 3. We ratio, then head out to grams. The last two problems, we did a step 1, step 2. Now here we begin with step 2, step 3. Let's write out, as we always do, the given quantity. We're given negative 1250 kJs. The 1250 kJs is negative because it's heat releasing, and I wrote down as the given quantity negative 1250 kilojoules of heat. We want over given. The first conversion is the heart of our problem. From the balanced equation, we want methane. Its coefficient is a 1. It gets placed on the top in the want position. Given comes from the end of that sentence, the delta H information. From the balanced equation, negative 890 kJs of heat are released. The want over given stoichiometric ratio is 1 mole of methane over negative 890 kJs. Now we need to go out one more step to change moles of methane into grams of methane. Mole times molar mass. Adding up a carbon and 4 H's gives me the molar mass of 16 grams per 1 mole. Starting in the heart of our problem, we hit on the calculator negative 1250 divide by negative 890 times 16. Ratio, then multiply, step 2, step 3. The mass of methane on our calculator, 22.47 grams. Grams will always come out positive. You've hit something wrong if you're finding for a gram and you get a negative answer. There is no negative mass. So the two negatives in exothermic simply cancel out to make a positive gram. You have now completed page 6. You are now assigned in your practice test A to complete objective 2. That is drawing the enthalpy diagrams, the first skill we practiced today. And objective 3. That is the stoichiometry that we've just practiced here on this page. Objective 2, practice test A, and objective 3, you now have plenty of information to try. Tomorrow we'll check your work. Well, not too bad for distractions, huh?